Sinai's theorem for random walk in random environment. So we are going to consider finally the case of a recurrent walk and try to prove a limit theorem concerning it. So let me recall you what we have proved so far. Okay. Okay, we had always assumed that this was negative. Okay, let's say that gamma star was the infimum over gamma such that E rho 0 gamma equal 1. Okay, so I write it this way so that gamma star can be equal to infinity. Okay, but in fact, I mean, in general, gamma star is the unique gamma such that this is equal to 1. Okay, but sometimes this set is empty. And we have seen basically so far 3 cases. So, okay, first thing is that when gamma star is larger than 1, you have a law of large number. Okay, so meaning that xn over n converges to some positive v. When gamma star is larger than 2, on top of that you have a CLT in the sense that xn minus nv smaller than n divided by square root of n converges to z, where z is Gaussian. Okay, and finally what we saw yesterday is that when gamma star is in 0, 1, okay, what you have is that limit when n goes to infinity of log xn over log n is equal to gamma star. Okay, and just to emphasize something, these results, okay, we have not treated the boundary case, and we have not looked at really the limit of log n over n to the gamma in the last case, but apart from that, they are somehow optimal, and maybe a consequence, I won't look too much into it, but like if you look at gamma star between 1 and 2, okay, if you remember what we proved yesterday was that basically if gamma star is between 1 and 2, there will be a potential barrier somewhere. Okay, so that there will be a passage time that will be long. So this thing, okay, this implies that there exists an x between 0 and n such that expectation x to x plus 1. Let me put a k here. Is equal to, is larger than n to the 1 over gamma star. I'll say minus delta to be on the safe side. Okay, this is what the potential barriers we will tell you. I mean, basically, what we had was something like the expectation of tau x plus a constant times log n. But if this is large, I mean, this is just the sum of some expectations. So one of the two has to be larger than, well, this power divided by log n, you absorb the log n, the delta. Okay, so what this tells you in principle is that you have absolutely no chance to prove a central limit theorem there. Okay, because basically to prove a central limit theorem, you need to make sure that basically you have no increment that is of order square root of n. Okay, and here you have an increment which is strictly larger than square root of n because gamma star is between 1 and 2. Okay, so this implies no CLT. Okay, and yeah, perhaps on Friday we will see a bit more about this regime in a very simplified setup. I mean, just looking at some of IID random variables that are heavy tailed. Okay, so now the question is, what about this case? And this case is, in fact, the main reason why I introduced the potential yesterday. So remember, Vx is the sum from j equal 1 to x of log rho j plus log omega x over omega 0. Okay, and yeah, this sum is yeah, it comes with a minus sign. Okay, if x is smaller than j. If x is smaller than if x is negative. Okay, so now if you look at well, at this case, basically these things are IIDs, they are centered, they are bounded, so they have second moment. So if you look at the typical behavior of your potential, well, it will look like a random walk on R, you know, with independent increment. You just have this thing that changes, but this difference here is bounded. Okay, so you will have something like that. And this thing here. Okay, and in particular, what you will have is that if you go at distance, okay, L, your potential will be of order square root of L. Okay, so basically, yeah, you know that the time you need to climb a potential barrier of a certain size is exponential in delta V. Okay, so basically, you're completely certain that you will not climb potential barriers that are higher than log n times 1 plus delta because of that in a time n. Okay, so therefore, with this picture, you know already that the walk is going to be trapped in a region of size log n square. Okay, so this is one first thing. And then within this region of size log n square, well, somehow, well, like yeah, basically the cardinality of the set will not matter very much. You have only log n square sites, so only the largest barriers will count. Okay, so basically, it's not too difficult to see that yeah, you will also need to visit. You will visit a region of size at least log n square. Okay, just because if you take a ball of size epsilon times log n square, well, you don't have big barriers to overcome. Okay, all the barriers you overcome them in a time n to the power delta, and you just need to travel log n square. So log n square times n to the delta is much smaller than n. So what Sinai's theorem tells you is much more than that. It tells you where you end up. Okay, and it turned out that okay, the result might be surprising at first, but in the end, it's kind of very intuitive why the result should be what it is. Okay, so let me write the theorem, and the theorem is somehow not complete because I won't tell you what Bn is. So I think things will become intuitive once we have the definition of Bn. Okay, so there exists Bn of omega such that this is due to Sinai in 81. Yeah, what you have is that the probability that xn minus bn omega divided by log n square is larger than epsilon. This is equal to 0. Okay. In fact, here, okay, here somehow, yeah, you have a. Okay, so basically on the scale log n square, I'm capable to tell you exactly where you are. Okay, there exists a site. Okay, so that well you are close to this site with probability. Sorry. Yeah, yes, the result was not very impressive. It was this is what the result is. So there exists a site around which you are located on that scale. Okay, and in fact, sorry. I know it's, yeah, you're right, it's equal to 0, yes. I'm sorry. Yes. Yeah. And I should trust my notes. And in fact, you can replace this with mn for any n that goes to infinity. For n for any sequence mn that goes to infinity. Okay, this would just make the proof more technical. The reason why I put log n square here is that bn is of order log n square. Okay, you will see. Okay, and yes, the second thing is. Okay, and this thing, I'm going to give you an idea of the proof, but I'm not going to prove it. But bn over log n square converge when n goes to infinity to something non-trivial. Okay, so I will tell you what this distribution is, but okay, there is no formula. Okay, I won't give you an explicit formula for this distribution. It turns out that the explicit formula for the distribution was computed, I think, 5 years later by Kesten in a separate paper. Okay, but okay, I guess you will be quite happy with the definition I will. Well, the definition I will give for this non-trivial distribution. Okay, so. Yeah, in order to get an intuition of where this Bn is, I will come with a definition, which is a definition of potential value. Okay, so we will consider V, which is from Z or R to R, and assume that V is continuous. Yeah, I think if you take the standard topology on Z, any function is continuous, so you don't have a. Okay, this assumption is just if V is defined on R. And I will define a valley for V. So A, B, C is a valley if, okay, so three things. One, A is smaller than B is smaller than C. Two, V of A maximize the potential to the left of B. So and VC maximizes the potential to the right of B. And the third thing is that VB is the minimum between X, for X between A and C of Vx. C, yes. Thank you. Okay, so perhaps let me draw a picture. A, B, C. This is the potential value. Okay? So I will define two other notions. So first is the depth of the valley. So depth of ABC. Well, it's basically the height you have to climb from B to get out of the valley. So it's simply the minimum between VA and VC minus VB. Okay, and the other notion I want to introduce is the difficulty of the valley. And the difficulty of the valley, it's okay. It's a max between two things. So it's the max of two things. The first thing is the max for X, Y, B, A of V, Y minus Vx. And the second one is the max between B, X, Y, C, V, I guess Vx minus Vy. Okay, so, well, you will tell me if this is right, but the difficulty is simply the highest potential barrier you have to overcome to reach the bottom of the valley, okay, from any point. Okay, so let's try to identify what we should do to prove Sinai's theorem, okay? No, you can, the difficulty can be 0. But you can take x equal y here, so you have 0. Yeah, so this is a, this is the value of 0 difficulty. Okay, so what do we want? We want to find A and B and Cn such that okay, so now V is equal to V omega. Okay, so first thing we want is, well, we want 0 to be inside the valley, okay? Okay, so this is condition 0, okay? The second thing we want is, we want that xn cannot escape an, bn before time n, an, cn, sorry, before time n. Okay, and the second thing is we want that xn reaches bn before time. Okay, so we want this to happen. Okay, we want the escape to happen with probability close to 0, and we want that you reach Bn with probability close to 1. Okay, so yeah, I mean, X wants to go where the potential is smaller. So yeah, a priori, I mean, unless you start very close to the boundary of the valley, you will try to go down first. Okay, so you will probably reach the bottom of the valley before you ever escape. Okay, that's so then when you want to escape, you have to overcome a barrier, which is the depth of the valley. Okay, so condition 1 should be that the depth of an, bn, cn should be slightly larger than log n. Okay, and we'll take a margin here. Okay, and the second thing, well, should be that the difficulty of an, bn, cn should be slightly smaller than log n. Okay, so here you have some freedom to choose things. What we will do in practice is this. Okay, so the idea is we will try to find a value that satisfies this. Okay, containing 0. Okay, it will have to check a bunch of other stuff, but and then we'll prove the theorem. Okay, using our intuition.
So V will be the V from before the sum of the.
V will be the V from before, and yes, V will be the thing from before. We won't use it. Yes. We will say, okay, we want V that satisfies some amount of stuff, and we will say, okay, with V that is taken as this, with expectation of log rho 0 equal to 0, it satisfies this stuff with a probability that is tending to 1. Okay, so what are we going to do? Well, okay. This thing is quite important. So, okay, what do you do if you want a value which is of order larger than log n? Well, what you can do, or log. Okay, let's say that you want a value which is of order larger. Okay, let me rephrase things. So this is our potential. Okay, okay, the idea is that if you have a requirement on the depth, there should be a minimal value that satisfies this. Okay, so we will try to get the smallest possible one. Okay. So let's see how we will do this. Well, there is one really trivial way to select a value. You start from 0. You say, OK, I'm looking at A of h. It's the max of x smaller than 0 such that Vx is larger than h. B of h, C of h, sorry, is the minimum of y larger than 0 such that Vy is larger than h. Okay, here we assume that V of 0 is equal to 0. Okay. Well, B of h is equal to, okay, it's, if you want, the mean of argmin V AH CH. Okay, what does it mean? What is argmin? Argmin is a set of values, a set of x's such that this is minimal. Okay, and possibly it has more than one value, so I take the mean of this just to take care. Okay, so I just fix a threshold x, h. This gives me ch, AH, and yeah, BH here will be here. Okay, and what I have here is that the depth of AH, BH, CH, well, this is larger than h. Okay, so well, clearly, okay, let's call this DH. Okay, so what you have is that DH, it's an increasing function of h. Okay, so if you want to be larger than, so what we are going to define is Hn let's see. I just want things to be continuous in the right direction, but let's see. So okay, so yes, it's not super. What do I want to do? Okay. Hn is the inf of H such that the dH is larger than log n plus square root of log n. Okay, and I'm going to take A n, B n, C n to be equal to A H n plus B n B H n plus, well, okay, A, B, C of H n plus. Okay, basically, this D of H, it's Cadillac, so it makes jumps in this direction. So, okay, inf of so at this point, you're lower than this. Okay? Just because of the discrete nature of the thing. It's not really important, okay? If V was continuous, it would be, if V is R valued and continuous, it would be, but here you have to take, is this okay? Okay. Okay, it's just the limit, okay, when H larger than Hn. H goes down to Hn. Okay? Okay, no, okay. I'm sorry, I should have done that. Yeah. Okay, and then I take this. Okay, and then you forget about this discussion. Okay, because this cannot drop. No. Yeah, no. No, this doesn't work. Okay, D can drop by a lot. Okay, because possibly just by going down, okay. Okay. Here, when you go past this threshold, at some point, you're just closing this part, and B jumps from here to there. Okay, so the depths jump by. Okay. So, okay, all these things don't happen in real life, but this. So, okay, because of this definition, this thing is trivial. Okay, this is true by definition. So what we have to check is that the rest is true. Okay, and okay, so yeah, what are the properties I want to prove? Okay, first thing, Hn is larger than square root of log n. Okay, I just want to make sure that the h is not too small so that I don't jump out immediately from 0 with some positive probability. Okay, the second thing is for epsilon positive, okay, what I have is that for all x, x minus bn larger than epsilon log n square implies Vx minus Vbn larger than square root of log n. Okay, square root of log n, you will see it's not something super important. It's just a convenient quantity in the computation, but you can choose something else. Okay, well, the third thing I want is that the depth of an, bn, cn is smaller than log n minus square root of log n. Okay, and the last thing I want is bn minus cn, okay, is smaller than log n to the 3. Okay, and
Part B. Set for epsilon. We have it's just a set.
yeah, no, this is just for all epsilon. If x is at a distance from bn larger than epsilon log n square, so if x is at, if you want, a macroscopic distance from bn, then the potential at x is slightly larger.
There's no epsilon on the right hand side.
No. No epsilon on the right hand side. You have a square root here. Okay, here you could have anything that is smaller than log n, and you could even have maybe a function of epsilon times log n, but you don't really care. It's difficulty. But I say difficulty, right? No? Yes, thank you. It's a difficulty. Okay, so these are kind of the desirable properties, and the lemma is that, well, for all epsilon positive, the probability that V omega satisfies A, B, C, D tends to 1 when n goes to infinity. Okay, so this is what we are going to look at, and the other thing we are going to prove, of course, is that if A, B, C, D hold, then well, P0 omega that P0xn minus Bn over log n square smaller than epsilon log n square, so smaller than epsilon. This is smaller than yes, than something that okay, well, this thing goes to 0. Okay, and combining the lemma and okay, so this would be lemma 1, and this would be a proposition. Okay, if you combine the lemma and the proposition, then you have the first part of Sinai theorem. Okay, and because I mean, what you're doing is you're just when you want to estimate this, you're just averaging with respect to E. So what you get is, well, first the probability that V omega does not satisfy the ABCD, which is something that goes to 0, because in that case, you don't know how to estimate this. Okay, and in the other case, you get delta n. So basically, you get the sum of the two, and they tend to 0. So is the plan clear? Okay, so this I will give you a very complete and thorough proof. Yeah, for the lemma, it will be a bit more hand-waving because basically it's a consequence of Donskoy's invariant principle and a few properties of Brownian motion. Okay, and I'm not going to define Brownian motion now, so basically, if you know what it's about, then fine, and if you don't know what it's about, it's fine as well. You just trust what I say. Okay, so why is this lemma true? So can I erase this? Do you have any question? So, yes, a fact, okay, it is that if you look at, okay, V, say, log n square t divided by log n, okay, you can look at this process, t larger than 0, t in R, sorry. And here, what I've done is I have extended V linearly, okay, between integers. Okay, so this thing, it converges in distribution as a process to dt t in R, whereas this thing is a double-sided Brownian motion. Okay, with variance. With variance, E log 0 square. But the only important thing is that the Brownian motion is non-trivial. So we assume that this is positive, okay, from the beginning. And the theorem is obviously false if this is not true. Okay, so we have this double-sided Brownian motion. And, well, what can I say about this process? Well, it's a random process and it's continuous. Okay, so, and the convergence in distribution is in the space of continuous function. Okay, so basically what this means is that you can couple these two things in such a way that they are close to one another uniformly on any compact yes. So okay, let me draw my Brownian motion. Okay, and okay. I won't draw my Brownian motion. I would rather, what I will do is I will look at each property and look at what should happen for the Brownian motion for the property to be true. Okay. So, because basically, what I hope, okay, what's happening here is that, yes, so a consequence of this is that AN, BN, Cn, okay, divided by log n square. Okay, this thing should converge. Okay, let me put something there. This thing should converge to A, B, C, A1, B1. Okay, C1. Okay, where A1, B1, C1 is defined as this thing. Okay, so I put something there because this is not necessarily true. There is something that could make this convergence fail. And okay, so basically, okay, this is your Brownian motion, okay. And yeah, you basically you want to lower the threshold here. No. This is not A1, B1, C1. Sorry. Yes, no, this is, yes. This is AH1, BH1, CH1 of B. Okay, you're playing the same game with the Brownian potential, okay? And you stop once the depth is 1. Okay, okay. So yes, this thing may not. So you have to check for some stuff, and basically what you have to check is that nothing crazy happens at H1. Okay, meaning you want to make sure that if okay, so basically here is your Brownian motion, and here is H1. Okay.
H1 is such that the depth is 1.
H1 is such that this is 1. Okay. A priori, I mean the depth can make jump. For the Brownian motion as well, yes. Yes.
Yeah, that's right.
Okay, so you have this possibility, and one might be in a jump, so the other possibility is this one. So, yeah, this is in a little bit. what you may have is, okay, here you have something larger than 1. And yes. Okay, and here you have something smaller than 1. Okay? Okay. So, yeah, we have to look at these two possibilities. These are basically the only things that can happen. Okay, so if you are in this case, basically AN, BN, CN will be located around here. Okay, and if you are over here, basically this one have to be CN. Okay, and this one has to be BN. And this one has to be N. Okay, because if you take things after the jump, you're already too small. Okay, so so I think basically this kind of tells you that this thing here converges to some functional of the Brownian motion. Okay, so this is already part 2 of Sinai's theorem. Okay, it's not an easy functional because you have this small thing to take care of. But, okay. So, yeah. Now, this thing, it would fail only if I wait up to height 0 for my Brownian motion, for the h to select the h of my Brownian motion when I take this process for the Brownian motion. So A is failing in the limit, okay. Yes, if h1 is equal to 0, but you see immediately that this is not possible. Because if you cut at a very small height, well, the depth will already be smaller than 1. Okay, just from standard properties of Brownian motion. B, okay, for B not to hold, if B has two equal local minima. Okay? Because basically, you need a point which is at a macroscopic distance from B, okay, where the potential is in the limit the same. Okay? But basically, you already know that this has probability 0, and the reason is basically the probability that this happened, it's the union over A, B, C, okay, let's say A, B, C, D in Q, that mean AB of B equals mean CD of B. Okay, and yeah, somehow if you condition to the value of BA and BB and BC and BD, these things, they are independent random variable, and they have their density. Okay, they have no atoms. So the probability that this occurs is 0. Okay. C okay, so C would occur if the depth of the Brownian valley is exactly 1. If the difficulty, sorry. Okay, but this is somehow not possible. Okay, why? Because having a difficulty of exactly 1, it means that you have a local minimum and a local maximum that are at distance exactly 1 in the Brownian motion. Okay, but so this means that okay, so this is the union over A, B, C, D of mean A, B, this is in Q, of B is equal to max CD of B minus 1. Okay, but yeah, for the same, this event has probability 0. Okay, simply because yeah, if you condition to anything that happens outside, you have 2 independent Brownian bridges. So these things, they have independent distribution and they are continuous distribution. Okay, and yes, this is not Bn minus Cn. This is Cn minus An. Okay, the width of the valley, and yeah, this converges to the width of the Brownian valley, which is finite. Okay, I mean, it's just the fact that yeah, Brownian motion eventually reaches 1 on both sides, so the valley is finite. Sorry?
Why is it cubed?
Oh, because it's because I didn't want to deal with. I could have said I need something that goes to infinity here to have a probability that tends to 1. Okay.
It should be bigger than log n squared.
Sorry?
Because it should be bigger than the thing on the right should be bigger than log n squared.
What should be bigger than log n squared?
Just log n.
Yeah. Anything bigger than log n squared works. Okay. It's log n squared times something that goes to infinity. Okay, so are you convinced with this? Okay, so okay, and yeah, so this thing converges to the location of basically, yeah, the minimal Brownian valley of heights of depths more than of depths larger or equal to 1.
And this convergence here from V to Brownian motion, that should be those curves.
Yeah, this is Donsker. Yeah, this is Donsker.
Is it doable?
It's just Donsker.
Try.
Okay, so what you have is that if you put V bar here, it's Donsker. Okay, and the difference between V and V bar, it's V bar is just a thing where you're not considering this term here. W x over W0. This is bounded by a constant. So this is just Donsker here. But I don't want to present a proof of Donsker theorem, especially without preparation. Okay, so yeah, I should keep these properties written, I guess, and use them to prove well, to prove this. Okay. This is. Okay, so I will have two steps in the proof. Okay, so let's. Two steps. The first one is to say that you reach Bn. So the limit when n goes to infinity of P0 omega. So we are assuming A, B, C, D. Yes, the limit of this to Bn is equal to 1. Okay, so you hit Bn. And the second thing you want to show is that the limit when n goes to infinity of P0 omega, knowing that to Bn is smaller than n, xn minus Bn larger than epsilon log n square is equal to 0. Okay, and then you combine these two things and you get the theorem. Okay, so yeah, we can start with this. Okay. And we are going to, for this, you need to prove two things, basically. You need to prove that, so, okay, let me. So you have 1a. 1a is simply we are going to show that P0 omega tau an is smaller than tau bn. Well, this thing goes to 0 when n goes to infinity. Okay, well, what I mean by that is that if these four assumptions that depend on n are satisfied, I have a bound on this that goes to 0 when n goes to infinity. So first, you reach Bn before you reach An with large probability. And second thing, the expectation of the, okay, what am I saying here? Okay, here, okay. I'm assuming that Bn is non-negative. If not, I will replace An by Cn. Okay? What's really important is which side of the valley I start on. Okay? So here I'm assuming that I'm starting on the left side, but there is no loss of generality if I start on the right side. So I'm assuming this. And I will show that this is, well, much smaller than n. Okay? So therefore, I know that this variable here is much smaller than n. And with large probability, it's equal to tau Bn. So I'm good. And the good thing is, now that I give you the plan, I won't do that. But I could leave it as an exercise because you know how to compute these things. Because we've done it. So let's recall how the computation works, and then we will see how our assumption. So this is A and this is B, and then we will see how our assumptions give the right quantitative things here. So okay, let's start with A. So A we will compute exactly this thing. I will just give an upper bound, which should be sufficient. So okay, this thing. Okay, we will define uj ux. I don't know ux. Okay, maybe uj because it will be like in the previous lesson. So uj is equal to ej omega tau an is smaller than tau Bn. And yes, so what we have is that for j in an plus 1, Bn minus 1, you have that uj is equal to omega j uj plus 1 plus 1 minus omega j uj minus 1. And this tells you that uj plus 1 minus uj is equal to rho j uj minus 1 minus uj minus uj minus 1. Okay, and yeah, using this, you can basically, using this and the fact that u of an is equal to 1 and u of bn. Sorry? It's a it's a probability. And yeah, perhaps just to be on the safe side, I will compute this and I will show that it tends to 1 because just to have something that aligns with the previous computation. And yeah, increasing is easier to deal with than decreasing. Okay, so what you get here, okay, is that ubn minus un, which is the sum from j equal an to bn minus 1 of uj plus 1 minus uj. Well, it's equal to, well, this thing is equal to 1. Okay, and it's equal to, okay, this thing here, I can rewrite it as the product. I'm starting from an, so from x equal an to j, I guess. Yes, rho x. And I have u an plus 1 minus un. Okay? So, this allows to get me an expression for uj in general. So what I have is that uj. So yeah, first I have an expression for, okay, this is just uan plus 1. So I have an expression for uan plus 1, okay, which is 1 over this sum. Okay, and this thing, I can rewrite it as exponential, and then this is nothing more than let's see. Well, I don't get rho an here. I start from an plus 1, right? Yeah, I start from an plus 1 here. Okay, and for this reason here, I get v bar j minus v bar an. Okay, where the v bar, you know, it's just as v, but I don't have this log. I mean, this v bar is really the random walk. Okay, so I have this 1 over this, and here I have the same thing, but the sum from I equal, okay, yeah, u of x, perhaps. J equal an to x minus 1 exponential v bar j minus v an. Okay, and I have to show that this thing converges to, that if you take x equals 0, this quotient converges to 1. Okay, meaning that the biggest terms that I have here, they are actually, they also appear there. Okay, so okay, now I have to check that I didn't mess up. Okay, so u0 is equal to sum j equal an to minus 1 exponential vj minus van. And here I have sum g equals an bn minus 1 v exponential vj minus vn. Okay, so I think the important thing is to check what's the biggest term here. Yes. Okay, you can simplify this, okay, and this makes things much easier. EVJ, and here EVJ. Okay, so here there are a few terms missing. Okay, but the thing is that the terms that are missing here, okay, they are, okay. So this is numerator plus. Okay, then the number of terms you have is smaller than log n to the 3. Okay, the number of missing terms, just because bn is smaller than log n to the 3. And the largest term is, well, exponential max v between 0 and bn, okay? But this thing is lower bounded by the difficulty. Okay, so, and here you have exponential of the depth. So this thing, okay, it's a little o of the numerator. It's little o of exponential v an. Okay, I mean, the key point here is that between the depth and the difficulty, you have a gap which is exponential square root. Okay, so that beats this term here. Okay? Okay. The key of this proof is that you have u0 expressed as this ratio, okay, and this sum here is actually, all the weight is around an. So u0 is close to 1. Okay. So let's prove B. So, yeah, for B, I want basically to, I would like basically a bound for tau bn, but it's just that I want to stop at tau an for some reason because basically the expectation of tau bn is infinite, and the reason is because at the left of an, you can find some very large traps. So the strategy would be to go at the left of an, find this large trap, and stay forever. And this makes the expectation infinite. So here you have an explicit expression for the expectation if you have this. Okay? And basically, if you remember the expectation, it was a product of rho going backward. And if you have this, there is no reason that your product will go before an. So this is the bound we want to have, basically. We want just to cut this thing and then show that this is, well, that the depths appear somewhere. You get the exponential of the depths and you're fine. Okay, so how does this go? yes, so the expectation of, so let's compute basically the expectation. Yeah. So we are going to compute this, and we are going to use a recursion, so make this index move from 0 to n. Okay, so this thing, to B, to A. Okay, let me drop the double subscripts here. Okay, so this is equal to 1 plus the expectation, okay, plus omega 0, the expectation. What do I have to do here? Let me check. Ah, yes. Sorry. Yeah, what I'm really going to do is this. Because what I'm going to compute is basically I will start from B minus 1. And, OK. So this thing I can. OK. I first want to show that this is smaller than the sum from x equal 1 to Bn of E x to x plus, okay, 0 to Bn minus 1 to x plus 1. Okay. So the idea is that this is true. Okay, well, to show this, basically what you should do is you say, okay, Toby, it's Toby minus 1 plus Toby minus 1. So I can say that this thing is smaller than Toby in tau A, is smaller than Toby minus 1 tau A plus Toby minus 1. Okay. Plus. Okay. I think, yeah, this is actually an equality. Okay, and now you can replace it by tau prime A, this, where tau prime A minus tau B minus 1, where this is first visit of A after tau B minus 1. Okay? You're just replacing tau A by something bigger. And if you do this, then you take the expectation and you use Markov property and you get that this thing. Well, it's smaller than E B minus 1 tau B tau A plus E0 tau B minus 1 tau A. Okay, and then you apply induction and you get this. Okay, so now we just care, I mean, here again you have log n to the 3 terms, so we just need to take care about all these terms and see if the maximal one is bad. Okay, and if we want to compute them, basically, yeah, we'll start with b minus 1 and go backwards. Okay. So what's the expectation starting from x of tau x plus 1 tau a? Well, this is equal to omega x. Well, this is equal to 1, okay, plus 1 minus omega 0, 1 minus omega x. And then here you get the expectation from x minus 1. And here you have tau x, tau a. Okay, and now doing the same thing as before. Okay, here I had omega 0 times 1 and omega x times 1, and here I had 1 minus omega x times 1, and just already put them together. Okay, so this gets me, okay, so I get omega 0, omega x times this. It's smaller than 1 plus rho x, and here, okay, I'm just using, here I have x plus 1. I'm just using this again, except that this one I have just a sum of lengths too. So this will give me, yeah, I went a bit ahead of myself here. I had no omega 0 here. I have 1 minus omega x. And here I have e x minus 1 omega tau x tau a plus e x omega tau x plus 1 tau a. Okay, and this gives you the right thing. So what? So this thing is smaller than 1 over omega x plus rho x e x minus 1 omega tau x a tau a. Okay, and you can iterate this, and it will stop when x minus 1, when x is equal to a plus 1, okay, because at that time this thing will be 0. This thing will be 0. Yes. Okay, so what you get is that E0, E x omega tau x plus 1 tau a, it is smaller than the sum. Okay, let me write it like this. 1 over omega x plus 1 over omega x minus 1 rho x plus 1 over omega, okay, plus. And the last term will be rho a plus 1, rho a plus 1, so yeah, rho x, rho a plus 1. So and maybe you want rho a plus 2, 1 over omega a plus 1 plus rho x, rho a plus 1. All good? Okay, so now we have a sum, and the number of terms here, okay, it's smaller than log n to the 3. Okay, so what I get is that E0 omega tau b tau a, okay, it's actually smaller than log n to the power 6 times the maximal term that I ever encounter. And the maximal term, okay, it's just a difference of potential. So it's okay, I have this thing here. It's okay. I'm summing. I'm taking the product from x to something, but the thing is backward. So what I'm getting is really exponential vx minus vy. Okay, where x is larger than 0. Okay, and y is smaller than x, okay, and larger than a. Okay, but the important is that x is larger than y, so this is smaller than the difficulty. Okay, so exponential log n minus square root of log n. And this is what we wanted. Okay, so for this first part, I mean, like these were just computations we did before. Okay, except that yeah, here you have this yeah, this little subadditivity trick. Okay, I think I will do a bit of overtime because there is absolutely no point in stopping the proof and taking it back on Friday. So let's now prove 2, which is somehow a bit lighter. So yeah, what's the idea there? Yeah, so if you want to go out of there, there are basically two choices. Either you end up outside of the interval a and bn, a and cn, sorry. And for this, somehow you have to visit an or cn at some point. Okay, and we know that it's not likely, because if you start from bn, you're not very likely to visit cn and bn because you have to climb too much. Okay. Or if not, you have to stay somewhere inside. And inside, okay, we are going to use the stationarity of mu to bound the probability of visiting each site. Okay, and this is going to be it. Okay, so let me write the details. Any question on the proof? So what's 2? Okay, so the 2, yeah, so what the first observation is I'm going to consider tau bn as a constant. It will be easier. So what I'm considering is I will say that P0 omega x n well, okay, xn belongs to A, okay, whatever A is, knowing that tau bn is smaller than n. Well, this is smaller than the max over k in 0n p0 omega xn in A tbn equal to k. Okay, this is simply because this is a convex combination of these things. Okay, and well, this thing here, it's p0 omega xn minus k, p0 bn x minus n xn minus k belongs to A. Okay, just because of the strong Markov property. Okay, so I'm just going to bound the probabilities that xm belongs to A, starting from Bn. Okay, and see that this bound is uniform, is good enough uniformly for all m that are smaller than n. Okay. Okay, so now, the probability is that xm, so starting from Bn, that xm does not belong to b minus epsilon log n square, b plus epsilon log n square. Well, it's equal to two things. So it's equal to it's smaller, okay, than the probability that, well, tau an tau cn is smaller than m. Okay, if I land outside of this interval, okay, plus the sum over an cn minus, okay, let's a c minus b minus log epsilon log n square, b plus epsilon log n square. PB xm equal x. Well, plus the probability that I land inside, okay, which is just this. Okay, so well, I already know, okay, from last time that the probability, okay, that tau A, okay, is smaller than m, starting from B. Well, this is smaller than m exponential VA minus VB. Okay, and this is smaller than exponential minus square root of log n. Okay, and the same for PB tau C smaller than m. Now for the rest, it's even simpler. Okay, what I have is that PB xm equal x. It's equal to delta B qm x. And this is smaller than, well, mu qm x over mu of b. Okay, delta b, it's smaller than mu divided by mu b, which is equal to mu of x over mu of b. Okay, which is equal to exponential Vx minus Vb, okay, which is smaller than exponential minus square root of log n. Okay, and again, we have less than log n to the cube terms, so we're good. Okay, so I think this is somehow the easier part. Like once you reach Bn, it's not difficult to show that you're trapped just because, well, you cannot go out of the valley, and inside the valley you can use equilibrium estimate if you want. So, okay, the first part is a bit more tricky. But the idea behind that comes from what we had proved before is that, yeah, basically, it doesn't take. Okay, so first thing is, yeah, when you look at the expectation of the heating time and you know these potential things, basically it tells you that. If the you will reach there before you reach there, okay? Simply because the obstacles you need to overcome to go there, they are always bigger than the one you need to overcome to go there. Okay, basically the next climb here is smaller than what you need to do to go to AN, so that you will do it before you go to AN. Okay, and eventually you will reach Bn. Okay, so this is what you can extract from the expression of these, gambler's ruin problem in a random environment. And then concerning the expectation of the heating time, basically, yeah, the intuition is that yeah, the time to overcome this is really like this lower bound is essentially sharp, okay, when this exponential of the potential barrier is much larger than the length of the segment. Okay, so after if you truncate the segment accordingly, this should appear. Okay, so the whole idea is that after introducing the potential, you somehow have a reason for the mysterious expressions you get for the expectation of τ1 and these heating time estimates. Okay, so we're even on time. Any question on the?
Just a very silly question. Mu is the stationary measure for environment.
Yeah. Yeah. Mu of x is just yeah, and yes, and this is it, I think.
And it's an exponential of minus.
It's the exponential of minus v. So this is, and vb is the lowest v, so this is good. Yeah, and the fact that you're down in the fact that you are in the valley basically tells you that yeah, this within this valley, okay, mu is concentrated on B. Okay, this is what one of our assumptions tells you. Our assumption tells you that it's concentrated on B macroscopically. In fact, it's even concentrated on B microscopically. Okay, so this is the reason why actually you can prove that, yeah. If you take any scale going to infinity, the probability is that, I mean, basically, the distribution of xn minus b is, of xn minus bn is tight. Okay, which is much more than what proves. Okay, yeah. So yeah, perhaps what I said about the Brownian motion was a bit confused, but I hope that the rest was clear enough. Okay, see you on Friday.